All right, so thanks everybody for joining, either here in the room, record attendance, I think here in the room, and otherwise online. Today we have a PhD student, Ginny Smith, who I'm very familiar with. I'm working with the high altitude ballooning projects. And today, high altitude ballooning trajectory prediction, including achieving an in-flight objective, is the title of our talk. So without further ado, I'll turn it over to you.
Okay, should I unmute my thing?
No.
Okay.
They can hear us.
They can hear us. Yes. Cool. Today this presentation, I'm going to talk through kind of the initial development effort and some of the results for this work. This work was previously presented at the Virginia Space Grant Student Conference here a few weeks ago. So this presentation is essentially the same, although I've added a couple of slides with new results. So really quick, what I'm going to be talking about, I'm going to talk through why this work is really interesting. I've had the question an unfortunate amount of times of like, why do I care about high altitude ballooning? So I'm going to talk through that a little bit. Talk through the basics of high altitude balloons. Not everyone is familiar with them. Talk through the flight profiles and specifically latex balloon motion models that are used in this prediction software. I'll talk through the methodology, both working from a launch location, but also working from an in-flight objective when you generate these trajectories. I'll also talk through kind of the initial verification, looking at the latex balloon motion models. This is comparing the predictions versus actual flights. And then finally, I'll cover a case study looking at an application of the in-flight objective capabilities for this software, and looking at NASA Space Grant's Nationwide Eclipse ballooning project, which is a pretty unique application, and you'll see why later in the presentation. So very briefly, to talk through the motivation of this work. So there's a high interest right now in actually looking at multi-vehicle missions, both for science, for communications, and a lot of other reasons and applications. And one of the main benefits of this is actually looking at cost reduction for your mission and also improved system performance. And in this case, from prior work, it was looking at disaggregating space systems and looking at rideshare opportunities on rockets. So these multi-vehicle, multi-platform missions, they take years and very specialized tools to actually plan and design these missions. And you have to be able to evaluate how well your sensors are going to work on Earth, or in the case of your figure on right for the Venus flagship mission, on a different planet. You have to make sure everything is going to work and you're going to get the data you want without actually having gone there and done this before. So one of the tools that was developed that kind of looks at this disaggregated space systems and technology is actually called Discotech. It was developed here at Virginia Tech in-house. You can see what it stands for there, but it was developed to simultaneously optimize orbital parameters for satellites, payload parameters, and payload distributions for space systems with multiple objectives. So basically what this work and what I'm going to be talking about in this presentation is aiming to expand Discotech, this tool that we have in-house, to be able to use for multi-balloon and also multi-platform applications. And this work currently addresses an absence of high-altitude balloon programs that are designed for optimization and integration into optimization tools. But also a lot of times balloons are forgotten about. You have satellite constellations, you have ground station constellations, but looking at how, what if you use balloons and had constellations of balloons instead? So that is the reason for this work. Moving forward, I'll be talking all about high altitude balloons. Specifically, there are 3 types that are focused on for this work. I'll be mostly focusing on the latex weather balloons here on the left-hand picture. These balloons are much smaller volume. They have kind of 2 or 3 primary stages. You have ascent, burst, and descent, or if you have a float, it's ascent, float, and descent, and I'll talk more about that a little bit. Typically, flights for latex balloons last anywhere from about 2 to 3.5 hours. Because you go until the balloon envelope bursts, you don't have extended flight time. For zero pressure balloons, which is in the middle, and super pressure balloons on the right, these balloons are both much larger volume balloons. Zero pressure balloons are actually open envelopes, so they are designed to be open to the atmosphere. So once you reach a specific altitude, it actually vents helium out so that it maintains a float, which is a constant pressure float. And those flights for zero pressure balloons can last anywhere from hours to up to a week if you have ballast on board. Super pressure balloons, unlike zero pressure, are completely enclosed envelopes. So you're not venting helium out during flight. You can see it on the right. They're often referred to as pumpkin balloons. They do look like pumpkins. These are also kind of your medium to large volume. They can lift up to 2 tons worth of payloads. The largest of these are about the size of a football field, to give you an idea. And they typically have a launch, ascent, float, descent, land events during their flight, and they can have flights that are hours to months. So you can have up to about 90 days worth of flight right now, especially with your ultra long duration balloons. So these are the kind of balloons that this work is going to be focusing on. In this particular presentation, I'm going to be talking through latex weather balloons. So your picture on the left, these are the balloons that Kevin mentioned in the intro, we are actually working on with students and doing flights with that. And so you'll see where that comes in a little bit later. But this is kind of the starting point for this work and the focus of the rest of this presentation. So there's a lot on this slide. You don't have to read all of it. Don't really pay attention to too much of it. But what I really wanted to talk through was to point out a couple of key assumptions that are being made for latex motion models that are actually being used in this trajectory prediction software. So the first thing, as you can see here, that all of the equations of motion are actually first order. They're not second order. So we are assuming a constant ascent rate that is defined by the user. The descent rate is a model described by NASA, a drag model described by NASA, but that is also essentially dependent on what altitude it is on the way down, and also what you expect the descent would be around sea level. But it is still first order. And in the case, if we were to float a balloon for latex, you have, in this case, constant altitude float, because the floats are short enough that that's an okay assumption to make. And so you basically just don't have a change in altitude for your vertical motion. Another assumption that you can make with these latex balloons is because they're small enough, you can assume that they move with a parcel of wind. And that assumption, basically what it does is it separates your vertical motion with your horizontal motion. So your dz/dt is not associated with your change in latitude or longitude during flight. Those are both still first order equations when you're looking at the horizontal motion, but that data is explicitly taken from GFS forecast data that provides UN to VWIN forecasts at different latitude and longitudes. There are a couple of other assumptions that I'm not going to cover now during this presentation that are addressed in the paper that covers this, and that a lot of other literature actually goes over and talks about kind of uncertainty in these equations, and goes into more detail about some of the choices for these equations. But when I keep talking about latex motion, latex balloon motion, these are the equations we're solving. They're first order. So one of the big aims for this work is actually designing high altitude balloon trajectory prediction software that you can integrate into an optimizer. So right now, a lot of the prediction software, especially for latex balloons that are commercially available or publicly available, are all web-based. It's a little bit hard to work with and integrate with them, especially if you're looking at maybe doing a flight objective or trying to achieve an in-flight objective. So this particular code was written in a way that it should be easily integrated with Discotech once it's been kind of fleshed out and the motion models have been checked. So very briefly, this is kind of how the functions look within the code. So you have your motion models in the top left. These motion models talk about those change in latitude, change in longitude, change in altitude. You have termination functions in the bottom left. These termination functions are what actually stops your code at stage from running. So if you're talking about ascent, that's usually a burst altitude is your termination. So when it goes above that, you've popped your balloon and then it starts the descent stage. On the right-hand side, you can see kind of what that stage pseudocode kind of looks like. So it's basically while that termination function has not been met, basically calculate your change in latitude, change in longitude, change in altitude, and then take that one step forward and calculate the next latitude, longitude, and altitude and time step for your balloon prediction. So this is the stage. On the next two slides, or in the next couple of slides, this stage pseudocode is what I'm talking about when I start talking through the different flight profiles. So I keep mentioning flight profiles. This is explicitly what I'm talking about. For latex balloons and even zero pressure and super pressure balloons, which see the float flight profile on the right. What the latex balloons typically do, and what we do here at Virginia Tech, is on your left, your standard flight profile. This has kind of two primary stages. You have your constant ascent, and then you have a descent stage, which is that drag model I mentioned earlier. It basically ascends until the balloon envelope pops, and then it descends until it lands. On the right-hand side, with the float flight profile, you have a constant ascent until a particular altitude. In the case of this code, you could also do time. But basically what it does is it vents out some of the helium and you achieve this constant altitude float until you send a cut down signal to your system, which allows the flight string to separate from the balloon and allows the flight string to descend under that same drag descent model. Typically your float is going to be at a lower altitude than that burst. For latex balloons, the burst is somewhere between 90,000 feet and 110,000 feet. For your float, you can float anywhere from usually around like 65 to kind of 85,000 feet is at the top of where you can just kind of open your balloon and vent. So these are the two flight profiles I'll be talking about in the pseudocode you'll see in the next two slides. Here. So this particular code, this is how it essentially works and what we're working from. So there are kind of two ways that you can generate trajectories. One of them is looking at from a launch location. So you're given a launch, latitude, longitude, altitude, and time. And from there, you create your trajectory for your flight. The next one that I'll talk about on the next slide is working from that in-flight objective. So this is kind of your standard prediction. This is essentially what we run when we're doing a flight. We do launch location, see where it's going to land. That helps us make decisions on flight day. On the left here, you have your standard flight profile, which is your ascent, pop, descent. And you can see you have your ascent stage here, which is that pseudocode I briefly talked through, and then your descent stage. On the right-hand side, you have your float flight profile, which has the ascent stage, float stage, and descent stage, as you saw on the previous slide. So what's new and exciting with this work is actually working from an in-flight objective. So this in-flight objective trajectory generation actually starts from that objective that is defined. It's usually a point during your flight. And you can do it both for the standard profile or for the float profile. In both cases, you start from your objective and you back propagate to get an approximate launch location. This is not the true launch location because the wind data you're using is ahead of what you're actually looking at for that time step. So it isn't quite right, but it gives you enough of an idea that it generates then a grid around it. All of those are propagated to the objective. It's then evaluated which of those trajectories gives you the closest path to your objective. And then that closest path is then forward propagated and continued through finishing your ascent stage and then through your descent stage. And the same thing for your float. It just assumes that objective happens in the middle of your float. So it starts in the middle of your float, back propagates, creates the grid, forward propagates, and then from there finishes the trajectory. So this work, a part of this work is going to be verifying the motion models that I've talked through. Right now, I'm looking at, this is kind of the initial results. And even then, it's kind of just the first couple of flights that I have to actually kind of start verifying some of this information. The 2 flights that you'll see in the next 2 slides actually were conducted here at Virginia Tech. One of them was on November 8th, this last fall, and one of them was just a couple weeks ago on April 9th. And essentially what looking at the motion models is doing is comparing if you have a ascent rate that's close to what your flight is, if you have a descent rate that's close to what your flight is, and your burst altitude is that happened on your flight, how well does the prediction actually predict where you're going to land based on those first order equations. So in this case, this is the November flight. You can see launch in the upper left-hand corner was from Kentland Farms, and the landing in the bottom right. And you can see in these 3 pictures, the actual flight path is kind of the coral colored, and the aqua is the predicted flight path. For this flight, the predicted flight path with these informed inputs based on the flight landed within about 1 kilometer of the actual flight landing location, which is pretty good. It's pretty good. Our second flight that we did here in April, not too long ago, was a little bit further away. The predicted flight path was a little bit different from your actual flight path, but there was a little bit of interesting winds that happened. And you can see here, especially towards your kind of burst max altitude here on the right hand side, they actually ended up doing a double loop-de-loop in the flight path. But because it was a very small loop, that the prediction only caught 1 loop. And so in the case of this guy with the informed inputs with respect to this flight, it landed within about 4 kilometers, which is still really, really good. So what this work is going to be continued. We will do several flights through the summer. Kevin is nice enough to have these flights where I'm flying a GPS logger. So the data you see from the actual flight path is collected on the flight that we're flying. And then I'm comparing it to the predictions that I'm running based on the forecasted data for the day. This work will have to be continued. Obviously, you want multiple flights. So not only will flights this summer happen and be compared and used for this work, but we're gonna have to look at flights all over the US because this particular region has very particular weather patterns. And so I can say, yes, it's very accurate for where we are, and in this case, where we're flying from. But you can't really say, yes, it's gonna work exactly the same in Colorado unless you actually look at flights there. So this work will be continued looking at flights across the US here. So that was the motion model verification for the latex balloons. Kind of this last big chunk that I'm going to talk about here is looking at initial results for a case study, which is the Nationwide Eclipse Ballooning Project. I'm very excited about this project. So this particular project is an application of achieving an in-flight objective, and here in a couple of minutes, you'll see why that's a very unique application of this particular type of methodology for this prediction work. So the Nationwide Eclipse Ballooning Project, for those of you who do not know, is a project that is funded by NASA Space Grant Consortium. The objective of this project is to live stream the 2024 total solar eclipse from the edge of space, which is from a latex high altitude balloon at around 70 to 80,000 feet. So they want you to be at altitude and live streaming video down to the ground for everyone to see. There are 30 plus teams nationwide that are different college, high school teams that are working on this project that are going to launch along the path itself. So it won't be all the teams launching in one location, they'll be launching along the path of the eclipse itself. And in this case, this eclipse totality only really occurs for a few minutes, like maybe max, I think 3.5 minutes, in each location along the path. And that changes depending on where you are. So in order to live stream totality from 70 to 80,000 feet, each balloon has a really small launch window to actually reach that objective altitude and also location under the path during totality. And so this application is very unique for the in-flight objective. We're reaching that altitude, we're reaching that time, and we're trying to figure out our launch location and our launch to help teams plan along the eclipse of where they can actually launch from to achieve this objective for the project. I will say really quick, so you can either fly for this project. They have the capability to fly a vent system, which means that you could achieve a float profile. So in the sense that you can either fly your standard float, your standard profile, which is your ascent, pop, descent, or you could do that float profile. So you ascend into that float, totality happens while you're in that float, and then descend. And so depending on whether you decide to do a standard profile or a float profile, it changes your launch location in some places, not in all of them. So this particular case study, for the sake of starting someplace, we don't actually know where all the teams are launching from yet. So this is just kind of a demonstration of this capability, is looking at 10 equally spaced objective points from southern Missouri to northern Ohio along the path of eclipse totality in 2024. This in-flight objective here is totality at 75,000 feet. We're looking at generating 3 trajectories. So one was that standard flight profile, the ascent versus descent, and then generated 2 different float profiles. One that was 30 minutes, so to just capture totality, and one that was an hour and a half. So the eclipse itself occurs way before and way after totality. So if you're looking at conducting additional science experiments or conducting atmospheric research, and you want to stay aloft and collect more data before and after totality, because the eclipse is still technically occurring, whether you can see it or not, then you want to look at potentially different float profiles, depending on your individual team goal. So for here, you can see at the bottom, the trajectory inputs was totality, time of totality, location for totality, 75,000 feet. There is an ascent rate of about 1,000 feet a minute chosen. That's a good rule of thumb of what to shoot for when you're working with latex balloons. Burst altitude is around 95,000 feet, which is pretty average for the balloons that we will be flying. And then also looking at that float altitude, which is in the case of the float profiles, which is your objective altitude at 75,000 feet. So looking at the standard flight profile first, you can see here the trajectories were generated at each point. In the bottom 2 pictures, you can see that for each trajectory, in this case, you get 6 of them to look at. The flight profile does put you at that objective location during flight, and it does occur at that time that it is specified. So you can see how the trajectories change. It was turned to make things fit on the slides better, but you have southern Missouri on your left, northern Ohio on your right. So you can see towards southern Missouri, you have a much more east to west, which in this case is west to east, top to bottom flight profiles, whereas when you get to northern Ohio, it's much more south to north. And that's just, you have different winds in different areas. So you can see here, in all the cases, you launch from the west and you end up landing east. But they do achieve the objective for your standard profile. Looking at your float profiles, they were also objective for all 10 points, generated for all 10 points. And in the bottom, you can see the profiles also achieved your objective at that altitude during that time, during your flight. In this case, it was assumed that your objective occurred halfway through your float, just for the sake of ease when doing the calculations. You can see that if between your 30-minute profile here in white you have, especially on the left-hand side, you have a much different launch location than you actually do for your hour-and-a-half float profile, which is your aqua. And so depending on what teams are going to fly, how many balloons they're going to fly, are you going to fly one standard, one float? You might have to launch from different locations. So this is a really cool application, meeting that objective in all of these cases of where do you actually need to launch from in order to be successful in this project. And here's a slide that shows you all three together. You can kind of see how they all cross at that objective point. And you can see you have much different launch locations and landing locations, especially in southern Missouri than you would in northern Ohio. So this is just very important for the teams all across the eclipse to know where they need to launch from, especially on the day of the eclipse. You might have crazy winds that you have to launch west of the path in order to reach that objective. And you might end up having to change that launch location the day before the flight or even the morning of, if it's cloudy or other things happen. So this tool and this methodology helps you plan a little bit further in advance, maybe get some ideas of weather trends for flights, and help you decide if you want to do a shorter float or a longer float, or even just stick with that standard profile for this project. So I will say that this work is, in this particular case study, is going to be continued. So in order to live stream the eclipse from the balloon, you have a ground station. And basically this work being integrated with Discotac, one of its abilities is to work both with satellites and ground stations. So what we'll be able to do is run a flight and be able to actually figure out maybe where a second ground station will need to be located. Instead of at launch, you'll end up flying out of range of your ground station at about 26 miles. And so potentially if you had especially a longer profile, like in southern Missouri, you might have to have that ground station at a different location. So being able to plan that is kind of the extending this to Discotac is what that will be looking at. So to kind of wrap everything up, this trajectory algorithm is ultimately, again, looking to expand Discotac's capabilities to look at multi-balloon and multi-platform applications. And for example, this case study on the nationwide Eclipse ballooning project, you have ground stations and balloons. It's also specifically designed to be integrated into optimizers, which is something that doesn't really exist at the moment. And you have, I talked through the initial verification of the latex balloon motion models, and that work will be continued, as well as looking at the case study and the initial results, looking at the nationwide Eclipse ballooning project with the different profiles. And as I mentioned, we'll continue this work. There's also going to be an effort looking into the computational cost of this algorithm. I am by no means a CS person or very good at coding. So right now, the algorithm takes seconds to run the way some of the calculations are completed. And so being able to reduce that cost so you can do hundreds of these runs in a much more efficient way. And then also adding both zero and super pressure balloon motion models into this. The idea and the general stage methodology will remain the same. What will be changed are those equations that get you your change in latitude, change in longitude, change in altitude for those balloons. So the framework is here. It's just adding the other balloon vehicles to this too. So a lot of references. And that is my presentation.
Any questions?
Sorry.
That's okay. Any questions here in the room or online? We have a couple of people online for Sam or for Ginny.
Yeah.
So many.
Okay.
So to start off, first, do you have any plans right now to have maybe like a zone where you could have to launch each of these different points at to make the balloon enter, for specifically the ones with the floats? Is there like a launch zone that you could incorporate such that it would still be at the projected point within a period of its float, maybe not perfectly halfway between.
Yeah.
But also within a certain like latitude, longitude region. Do you have plans to integrate like that kind of error analysis sort of with it?
Yes.
Okay.
So one of the things, especially when you're looking at these predictions, is they aren't exactly perfect, right? There's a lot of uncertainty to it.
By the way, 1 kilometer is badass. Nice job.
Yeah, I was really excited about that. So there's a lot of uncertainty in this. I really didn't cover any of the uncertainty, but there is a significant amount that you cannot really ignore. So being able to create either launch zones for your float, or even kind of as long as you launch within this area, you'll be in totality within a certain amount so that you'll be under totality there. Basically to give like that latitude and longitude might be on a lake. You don't want to launch on a lake, right? You want to be able to launch from a park or from a school or something like that. So integrating something like that would be a lot more practical for choosing those locations and still knowing you can achieve your objective. So yes, that will be added. It just isn't right now.
Okay.
So.
Yeah, no worries. 2 more now. I'll save the rest for after. The second one is going back to your motivation with having say extraterrestrial balloons. How would you be able to make your model more robust to plan for weather patterns that we know very little about?
So a part of that work would probably be, especially for example, Venus, which will probably be one of the case studies I look at with Discotech. They have orbiters, they have small sats, they have the aerobot, which is your balloon, and they have a lander, I believe. And so having those different types of vehicles, you don't know what the atmosphere is. I will say though that especially for Venus in particular, above its really dense cloud layer, it's about Earth atmosphere at around 70,000 feet, which is pretty awesome. So you can actually do a lot of technology testing on Earth or Venus. In terms of modeling the weather patterns, a lot of this, right, is, it could be this, but it isn't necessarily going to be. So some of that is going to be injecting uncertainty in the models themselves. I will never have a perfect model of Venus's atmosphere. So it is with that understanding that this is a rough model, this is something that could be done. I do not work in NASA, so I don't have access to their big models. And nor do I think it would be practical for something this far out to handle that. But in terms of evaluating sensors, evaluating like what are your limits for spreading between for the data transference and things like that, is where this is going to be useful, not necessarily in like those exact weather patterns. So finding the limits of your design, not necessarily designing for like very explicit environmental patterns.
Okay, and last question, I promise, is just, I guess, wrapping my head around this. When your balloon goes up and it pops and it comes down, it's a very uncontrolled, it's sort of controlled by, drag, but
Yeah, we have a parachute, yeah.
it just lands somewhere.
Yep.
And like, do
Yeah.
you have to get like prior permission from like said area? Like, hey, it's gonna land somewhere. Okay, where? I don't know. Okay, can we just have it land in your vicinity? And then you get like a yes or a no. Is that how it works? Or what?
So it's a little bit of a different process than that. But that's actually not like along the wrong lines. So what we do is in preparation for these launches, we run these predictions, especially with like 1, 2 day, 3 day out forecasts with GFS. Pretty accurate enough for us to put us in the neighborhood of where we think it's going to land. The FAA has some guidelines that we fly under. A couple of them being don't land in a populated area. We have kind of internal ones like don't land in a national forest because that's really hard to get. So we tend to try and fly with flight tracks that don't put us in the Atlantic Ocean or don't drop us in West Virginia National Forest, which is what I was looking at last weekend actually. So we had one flight we were looking at was dropping us in Charlottesville, so we couldn't fly. So you make decisions like that based on big cities. For small towns, you have an idea of where it's going to go, but you don't know exactly So as you drive, when we have trackers on board, so once we get that like, hey, it's landed ping from the trackers, what we do is we drive out to the property, we look for the property owner on GIS and try to contact the property owner. And then from there, we talk to neighbors and see if they have availability. A lot of times owners are super cool with it. They're, a little bit, why do you want to come on my property? And then it's a science experiment for Virginia Tech. They're usually like, oh, cool. And you have GoPro footage and stuff that they can look at. So they're usually pretty into it after a bit. But yeah, we don't have control over where it lands.
Yes.
So our first flight here landed how many feet up in a tree? About 50 feet up in a tree. And it took three hour, like out 3 hour back trips to actually get it back. We spent 2 hours sawing down the limb that it was stuck in with a 40-foot pole saw. We've also had a couple really recently that have landed in front yards, and actually people have seen them come down. In both cases recently that I'm talking about, a kid was outside playing and they saw it come down, which I'm jealous of. We had one land in some like brambles. I've had all kinds of other experiences that I can regale you with stories for. So a lot of it is you hope it lands in a field, you hope it's easy to get, you hope the owner's there. Sometimes it can be a little bit of a longer recovery process. But
generally, I'd say that the thing with that is the US government and the FAA, since these are unmanned just free balloons, there's no way to control that kind of trajectory. So it's with the understanding, like basically there's a general understanding like when you're doing this, like you might be what to do. So yeah, so that's why there's no like before you even launch like information. Two, we're doing them on more of the hobbyist, like amateur side. So the understanding is they're small enough that when they do come down, they're not going to be damaged.
Cool.
I say that as in contrast to bigger flights when they have that. That's a different-ish story.
consideration.
Yeah,
Yeah, you have to be really careful when you cut down.
so they control where they cut down, so they make sure it's not somewhere. But even then, it's still a similar process of they just come down in some person's field and they go and be like, hey, can we go get our plane? Like, yeah, sure. That stand of beans wasn't any good anyway, so feel free to like mow them down or something.
Yeah.
Cool.
There is work that I will say that has like not guided, but like controlled paragliders and stuff. We don't do that. It's very hard on the control side.
Yeah.
I'm not a control person, so we don't have that. You also have to get special permissions to do that, because it's basically you cut down target a location. Not typically, a little bit frowned upon. But there has been work that's done and published that people have done that for.
All right, I yield the floor for one. Thank you.
Any other questions?
Yeah, so you were saying that, you have these 2 test flights that you were able to like validate your model on. Do you have plans? It sounds like you have more launches coming up with summer, but do you have any other plans with other people who launch balloons in other parts of the country and like validating different things, or
So
is that still like
I have not reached out to anyone else. That would be a good place to start for other people who have done. Not every place is flying a GPS logger that records your data every second. In this case, just switches overkill. But there was a 2017 version of this project for the 2017 total solar eclipse. At the time, there were 60+ teams, and every team flew an Iridium tracker that all beaconed their data to a singular server that Montana State had. And so what that data is still available, you can still, or I believe it is, you can still go pull the flight tracks. So I could pull launch locations and make some assumptions about the inputs based on the flight track itself. But then use that data, which was, West Coast, East Coast, right? So all across the US, 60+ teams worth of data to look at. In terms of like other individual schools, there's not a lot of work right now to like target individual schools. If it's needed to get more data, that's kind of what we'll step to, but right now I think there's enough available data to say these are good enough and put you in the neighborhood. The real trouble is actually going to be for the zero and super pressure balloons, because those are more commercially flown, which means that their flight tracks and stuff are not available online. So there's going to be some effort put in to try and find the tracks to be able to compare predictions to. There are some available, but it's like a handful of ones that I've seen in papers. They're years old. And so trying to get these big balloons go up all the time. And you don't need anything about the payload, you don't care about any of that. You just care about the flight track. So let's see if we can get some of that data.
And the second half, when you were talking about your 10 different points and kind of figuring out where you launched to hit that eclipse, was the cone that that was like being wrapped against like the ground tracks, was that like the path of totality?
Yeah.
That thick, or?
Yes. So that is the dark part here on this graphic is the path of totality. So by no means do you have to be on that center line.
On the blue line.
Right.
Yeah.
So talking about kind of a swath of reaching your launch locations to your objective, there's also going to be a swath of acceptable objective points to be able to hit for this particular project. I will say you don't want to be on that edge though. You want to be within totality. And so there's probably, it wouldn't necessarily, the boundary for that swath wouldn't necessarily be the edges, it would be some distance in from that. But I will say from my prior experience, we were pretty close to the center of that totality. It was really, really cool looking from the balloon. And so I think a lot of people, it's a lot safer to target that. And then if you miss, you're still there. If you like overfill the balloon or underfill the balloon, you can still achieve your objective. So yeah.
So, but you don't have to be super precise on that.
Right. So it's like
your objective.
I mean miles.
Yeah. Okay.
So like in this case, in this picture, you could be launching from like the western side and still hit that middle. You can kind of see here, right? You can launch like as far away, as long as you don't have to hit that center line for your objective. Maybe you're looking up here, so you can launch from outside. I will also say that like the benefit of this project is experiencing a total eclipse.
Yeah.
So it would be nice to also be under the path of totality when it occurs. Yeah. And so if teams have to launch outside of totality, it's probably going to be a little over an hour before flight or an hour before totality that they launch. So you can pack up in that time and move to totality, hopefully, or have a plan to do that movement because roads are going to be insane. But that's a part of this huge planning effort that like is very kind of a very unique thing that happened, right? Because people just pull over the side for totality and then wander off. And so trying to be able to be safe while having your balloon in the air while recovering and everything else too is crazy.
Did you participate in the 2017?
Yeah.
Eclipse? Okay.
So I was at the University of Kentucky
Okay.
when that one occurred. So I have experienced something like this. I haven't done the annual eclipse. So there's an annual eclipse in October. That is our practice eclipse for the 2024 total eclipse. And so we will be traveling with a small team of students out west to actually be able to, let's see if I can, here you go, you got your paths. So we'll be able to test all of our equipment, test our procedures, test this software to see, yes, we launched at the right time to put us where we thought it would. So
Cool.
yeah.
Congrats.
So for October, we're looking at launching from Roswell.
Oh, okay.
We're gonna have some fun. We're also driving, so it's gonna be a little bit of a trip. But for the April eclipse, we're either looking in Illinois, around Champaign potentially, or Arkansas. There's so some businesses and museums and things basically say, we heard about this project. If you all want, you can launch from our property. And so in some cases, there are people that are saying, if you want to launch, we're in totality or whatever, then you can come and set up and use our facilities. In a lot of cases, we look for schools first, because it's a huge part of this project is educational outreach. And so you're looking at how many people can you reach, as well as like, hey, look, cool balloons. Hey, look, live stream video. So that's kind of the whole point of this project, and it's really cool. And it's a very unique thing. So the next total solar eclipse across the US is not, at least for a decade. So this is a very unique, very, very, very cool project for right now. Minus 1 year, yeah, a little bit less.
Yeah, the ones.
It's like a week over, or 2 weeks over the 6-month mark from October.
348 days.
Nobody's counting. We're not worried about
We're
that.
not being that far.
We're not that worried that we only have a year to get all this stuff working.
So there will be somewhere between 4 and 6 flights that occur this summer in preparation for the 2024 eclipse, and the 2023.
Yeah, even
But
October.
I mean, both of them, to test all the hardware they're giving us, test our own hardware, make sure ground stations work, actually see what that range is.
You have samples of what they'll be giving you already? Is that
We
hardware?
know what payloads they'll be giving us. We do not have all of them in hand yet, but we are assembling everything. So we are getting bags of screws and Raspberry Pis, and like, here's a screwdriver to like put everything together, and nothing is soldered, so it's like a big build.
More so, yeah, with these test flights, it's more of, Jenny is talking about testing procedures and doing that, especially. One thing, that we could talk about is what happens, or one of the limitations with flying is having cloud cover. So if you have more than 50% sky covered with clouds, you're not supposed to launch. They're looking at maybe getting waivers for that, because what we're interested in, it doesn't matter if it's cloudy or not. And so not only like looking at the path prediction, but what are the reasons of like picking out several different ones is what if, we're saying Roswell, but then what if we have to go to like, Western Texas, because Roswell's going to be bad for launching. Yeah.
And you won't really be able to even start making those decisions until about 3 days before. And like truly say, we are launching from here the day before.
So if you get a waiver to fly in intense cloud cover, you then have to file a flight plan. So that way, if somebody, like some pilot flying IFR doesn't know.
So I will say one of the things, so we're flying the Iridium tracking, so that is open for the FAA to be able to track our balloons themselves. So if it happens that they enter an unsafe situation, they can contact us, and we will have a cut down on board, so you can cut it down and basically take the flight straight down.
Okay.
I don't believe that happened during the 2017 eclipse at all. There is significant increase in flight traffic, especially with small planes for the eclipses, especially at small airports. And cell phone traffic is another fun thing, because there's so many people in one space. You have to get priority cell, basically service, for them to be able to contact you.
Yeah.
So, but yeah, so that is a built-in safety measure of this project.
Any other questions online? I have a couple of people online, but are there any other questions here? Nothing else? Yeah, but we could probably continue the discussion here, but I'll sort of end it for now, as far as a formal sense, and not keep the couple of people online. So thanks everybody for joining here, and we'll pick up again. This is the last one for this academic year. Thanks for everybody who's presented so far, and we'll look for more presenters starting in October or September. I guess more in October. So thanks.